Here, I want to give you some guidance on developing an analytical solution for the fully developed flow in the cylindrical annulus, which is required for the project. And so essentially for fully developed flow, and let's consider a cylindrical duct first, and then we will consider extending it to a duct that's a cylindrical annulus. So you have uniform flow coming in, and then after a while the flow becomes fully developed, and then you'll get the parabolic profile, and when that happens the velocity won't vary in the axial direction. And so in the fully developed region you have an analytical solution for the parabolic profile, that is, you can solve the equations by hand. And you want to compare that solution to the Ansys computational solution in the fully developed region. And the way you develop this analytical solution is you write the governing equations in the cylindrical coordinate system. And most of the terms will be zero. So if you look at the governing equations in vector form, so you have conservation of mass, that's continuity, and you have F equal to ma. And this can be written in Cartesian and cylindrical coordinate systems. So if you look up on the web, you will see the Navier-Stokes equations in Cartesian and cylindrical coordinate systems. So to develop the analytical solution, we have to use the equations in cylindrical coordinate system, which I'll indicate what they look like. So the cylindrical coordinates, if I have my duct and if I take a plane like that, the axial coordinate is usually denoted as z, and the radial coordinate is usually denoted as r, and theta is a circumferential coordinate. So instead of decomposing the velocity into the x, y, and z directions, which we do in the Cartesian coordinate system, we decompose the velocity in the radial into a radial velocity, axial velocity, and circumferential velocity. This is like a swirl component that will be zero. And so if I take a location like that, my axial velocity v sub z is going to be in that direction, and the radial velocity v sub r is going to be in that direction, vertical in this particular plane. And in fact, in the fully developed region, the radial velocity is also going to be zero. So you only have the axial velocity that's non-zero. And so the governing equations here, let me put down the governing cylindrical coordinate system, and I have not included the theta terms here. And if you look at this set of equations for in fully developed region, I'll highlight the terms that are non-zero. So the pressure can vary in the axial direction, and the axial velocity can vary in the r direction. So those are the only non-zero terms. Everything else is zero. I won't go through the reasoning for that. You can show that all this is zero, and in fact this equation says that dpdr is zero. There's no variation of pressure in the radial direction. You can also show these terms are zero. So you get two non-zero terms, and you integrate that simplified governing equation and apply the boundary conditions that the velocity is zero at the wall, and then the gradient is zero at the axis, and you'll get an expression for the axial velocity. So you'll basically get an expression for the parabolic variation, but it'll be in terms of the pressure gradient. However, what we know is the inlet velocity from the boundary conditions, not the pressure gradient. The two are related. So if I increase the inlet velocity, I'm increasing the pressure gradient. So I want to know, hey, I want to get the expression in terms of the inlet velocity. So how do I do that? I relate the pressure gradient to the inlet velocity, and I do that by integrating that parabolic profile in terms of the pressure gradient over the cross section. And so let me explain that. First, I'll do it for the cylindrical duct, and then you'll see it's it's relatively, at least conceptually, straightforward to extend it to the cylindrical annulus. So first, let's take this case. The mass flow rate is the density times. So over here, since I have uniform velocities, so the average velocity, the velocity coming in, that's our boundary condition times the cross-sectional area. Now the mass flow rate over here has to be the same because the mass flow rate at any cross-section is the same. And that I can find by integrating from 0 to r, or in this particular case, it'll be from R1 to R2. So I have to integrate across the cross-section of the inlet, of the parabolic variation times 2 pi r dr. Now this variation is, is right after the integration. It'll be in terms of dp dz, and so once you do that, you will get an expression. Once you do the integration, you'll get an expression relating dp dz to the inlet velocity. And so if you do that for the cylindrical duct, I'll show you what the final result looks like. It looks very simple. This is the axial velocity, so this variation here over this inlet velocity, it's just given by that. So for instance, if the inlet velocity is 1, what this says is at r equal to 0, that is on the axis, it has to be 2. So if I go to, if this is 1, so that's 1, this has to be 2. So the maximum velocity will be 2. So I suggest you do this for the cylindrical duct first, and then extend and check that you're able to get this expression, and then do the same thing. When you're doing the integration, you will do it from R1 to R2 for the cylindrical duct, for the cylindrical annulus. And then the wall shear, once you find the velocity profile, it's just mu, the gradient of Vz in the r direction at the wall. And so that way you can get the wall shear and then compare it to the Ansys result. Hope that was useful.